Okay, now when you're in Year 9 and Year 10, you learned a little bit about particles and the electrons and how they're arranged in the shells around them. Now, in the outer shell, the valency shell as it's known, if it was in group 1, for instance, you knew that it would have one electron in its outer shell. If it was in group 2, it would have two electrons in its outer shell. And if we kind of ignore these ones through here and just go straight over, these ones have 3 electrons, 4 electrons, 5, 6, 7, and 8 electrons. And when we taught you about ions, the basic understanding was that anything in group 1 would lose an electron and get a charge of +1. Anything in group 2 would lose 2 electrons and get a charge of +2. Anything in group 17 here would gain an electron to get a full outer shell, and that would be -1 because it gained a negative electron. And anything in group 16 would gain 2 negative electrons and have a charge of -2. And aluminium, you're aware that that would lose 3 electrons and have a charge of +3. Now that was about the extent of understanding that in maybe Year 9 or Year 10. And with drop-in swap, you learnt how a metal, which is on the left. Now when we're talking about metals and non-metals, just a quick reminder that if you look at silicon and aluminium here, if you then do a staircase, that separates metals and non-metals, with this area being metals, which is by far the biggest, and the non-metals on the right. So you learnt that when you had a metal and a non-metal coming together, you had the positive and negative attracting, and that formed an ionic bond. So those were ionic bonds, and the way you recognise those was that there was bonding between a metal and non-metal, so you had to be able to identify them. Now hydrogen is always considered a little bit unusual, but it's often put in the middle here because even though it has one electron, which you think would make it go into this group 1, it is actually a non-metal, so often it's placed in this middle area. So that's why it's there. Anyway, ionic bonding is due to the electrostatic attraction. Now electrostatic attraction is a fancy word. The attraction between two ions. So this is a positive ion, and that's a negative ion, and they're attracted to each other because positive attracts negative. And we'll learn about how they form ionic compounds in more detail later in this course, but all you need to know at the moment is up to now most of the information you've had on bonding has been to do with positive ions and negative ions being attracted to each other and forming ionic compounds. And when you did the formula with drop-in swap, you were writing the formula for an ionic compound. Now in Year 12, we're going to do something a little different. Because when you look at the periodic table, all we've really talked about at the moment has been metals here and some ions that form in here. That's what most of it's been about. And if you've been thinking about it, you may think, well, what happens about these guys in here or these guys in here? And there's all these other situations which we never talk about. Well, these atoms do combine with other atoms to form compounds or molecules, but the kind of bonding they have isn't quite the same. Because what happens in ionic bonding, it's not just a matter of these guys losing electrons. What it really is that these guys are so strong that they actually take the electrons off the metals. So it's more a case of them losing it when they're near a non-metal, which is, and that strength has a special name. It's got to do with something called electronegativity. And you'll come across that later in this course as well. But you may have wondered, what do other atoms do? Well, the atoms in the middle area, and this is the kind of area we're talking about in here, this area is a little different. These are actually all metals, and they have a different type of bonding as well, but there's a very common kind of bonding which we haven't taught you about, and it's called covalent bonding. Whereas between the metals and the non-metals, we get ionic bonding. When you get non-metals by themselves, sulfur and phosphorus and nitrogen, oxygen and carbon, when these guys are just by themselves, they can't actually take electrons off each other. They do something a little bit different. they share electrons to make something called a covalent bond. Okay, and in doing so, they get a full outer shell. Now, one of the important things in understanding this type of bonding is to be able to draw Lewis diagrams, and that's what we're going to be doing next. But all you need to appreciate at this moment is that covalent bonding occurs between nonmetals, and the one way of recognizing that it's going to be covalent bonding is just being able to spot that they are both nonmetals. And that division between aluminium and silicon in that kind of staircase manner as you go down is one way of recognizing it. Okay, so for instance, in the following example, which would be ionic and which would be covalent? Okay, well, magnesium is a metal and oxygen is a nonmetal, so that would be ionic. CH4, carbon, is a nonmetal, hydrogen is a nonmetal, so this would be covalent bonding there. Iodine is a nonmetal, and there's just two of them, so the bonding between those two atoms would be covalent. H2O, H is a nonmetal and oxygen is a nonmetal, so this would be covalent. Aluminium is a metal and oxygen is a nonmetal, so that would be ionic. Sodium is a metal and bromine is a nonmetal, so that would be ionic. Okay. Carbon is a nonmetal and oxygen is a nonmetal, and that would be covalent. Okay. Now what's actually happening here is if we have a molecule H2, hydrogen only needs 2 electrons to get a full outer shell. Now we're used to thinking of 8 electrons being necessary. But remember, when we have the orbitals, the first orbital contains just 2 electrons. Remember, you have 2, 8, 8. So the first orbital only has to contain 2 to become full. And that's why hydrogen can exist with H2 and be happy. So when we look at this electron, the dot electron comes from the hydrogen on the left, the cross electron comes from the hydrogen on the right. They both contribute an electron to this bond in the middle, and so those 2 electrons are sensed by this atom, so it's got a full outer shell, but they're also sensed by this one, and it feels like it's got an outer shell. And the sharing of those electrons is how they establish a full outer shell. Now if you have another look at another example, Cl2, a similar thing happens. Chlorine has 7 electrons, so 6 of the electrons, and they usually, in fact almost always, are placed in pairs like this here, are placed around this atom. So that's 2, 4, 6 electrons, and it puts 1 electron into the shared bond in the middle, and it's got 2, 4, 6 here. So this atom here senses it's got 2, 4, 6 and 8 in the middle. So these 2 contribute to the electrons for both atoms. So it gets its full outer shell by sharing those 2 in the middle. Okay. Now, just a point here, even though we're showing these as dots and crosses, for many years now it's been a common practice to show all electrons as dots and not crosses, although that's beginning to change, and there's some reasons for that, but that's not important at the moment. Okay, but as long as you understand the basic concept of sharing electrons between non-metals. And the next step on this is drawing Lewis diagrams.